Okay, well, thank you very much. So you see the title of my talk. And so this is part of a joint paper with Tomer Schlank that should be on the archive soon. And there's lots more in the paper that I can talk about in 20 minutes. And so first thing I want to do is a little bit of history. Okay, so let K be a number field, and then X over K a variety. And then the basic question one likes to answer is how to determine if there are no rational points. Because of course, technically, if there are rational points, we can write one down. But if there are none, how do you prove that there are none? And so one thing that you can do is you can show that there are no adelic points, which usually happens by showing that there are no points modulo n for some n. So this will imply that there are no rational points. And then the local global principle is about asking, can you go the other way? Okay. And early in the 20th century, there were some results saying that you, in some cases, can go the other way. And people sort of wondered to what extent you could always go the other way. Okay. Now, there were some counterexamples found by Lind and Reichart in the 1940s. Okay. And what they did is they found counterexamples. And the question that interests me is how did they prove that their counterexamples had no rational points? And so in this case, they used quadratic reciprocity to prove that there were no rational points. Okay, and I should also say that there were examples of Selmer, which of course led to Selmer groups. But that aside, when you think quadratic reciprocity, okay, that's a special case of class field theory. And so if you want to make a more general method for proving that something does not have rational points, well, Yuri Manin in 1971 was able to use the power of class field theory via the Brouwer group. Use class field theory via the Brouwer group. And because in class field theory, there is, the Brouwer group is H2 of your spin in the Untitled topology with coefficients in GM. And the point is that there's a local global principle for the Brouwer group over number fields, which is equivalent to some of the non-trivial parts of class field theory. Okay? And so, more specifically, what Manin did is he defined in between x of k and the set of adelic points, x of ak, defined an intermediate set called x of ak yar, okay, such that even when x of ak is, and they satisfy these inclusions, and so even when x of ak is non-empty, x of akbr can be empty. So can be empty, okay, even if this can be empty, even if this other thing is not empty. Okay? And in the particular examples, say of Lind and Reichart and of Selmer, this actually works to show that there are no rational points. Okay? So then, Skorobogatov, based on some examples where the Brouwer-Manin obstruction did not work, in other words, so in cases where the set of rational points is empty, okay, but the Brouwer set is non-empty, so not equals to empty set means non-empty. And so in these cases, what we can do is we can use another obstruction defined by Skorobogatov, which is always a subset of the Brouwer set, and as he showed, sometimes gives you more information. in other words, sometimes proves non-existence of rational points, even when the Brouwer set does not suffice. Okay? Now, he was able to explain, I believe, all the counterexamples for the Brouwer obstruction that people had at the time, all the examples in which the Brouwer obstruction did not give what people wanted. But there was a question, is Skorobogatov's a tall Brouwer obstruction sufficient? Okay, in other words, for any variety that has no rational points, does it show you that there are no rational points? And unfortunately, as was shown in 2008 by Bjorn Putin, also my thesis advisor, Putin found an X such that X had no rational points, okay, but the tall Brouwer obstruction did not suffice to show that there were no rational points. And since then, various other examples have been found by other people, but Putin's was the first example. I should also remark that just as the Brouwer-Manin obstruction uses the Brouwer group and class field theory for the Brouwer group, Skorobogatov's obstruction uses both the Brouwer group and descent on finite atal covers, sort of together in unison. Okay? And that's all you have to know for now. So now what I'm going to do, now that I've given a little bit of the history, is I'm going to talk about the specific example. Okay? We call it Putin's counterexample because it is a counterexample to the hope that the Atal-Brouwer obstruction always explains the non-existence of rational points. Okay? So let's give some details of the example. So there's going to be some X. I use the notation X up here. And in this case, so X is going to be fibered over a curve. C is going to be a curve such that C, it doesn't have no rational points, but it has finitely many rational points. Okay? Now you might think, okay, just simply all you have to do is take a higher genus curve, but actually one of the more interesting cases is when C is an elliptic curve with rank 0, okay, which you can also do. And so X is going to be three-dimensional. Oh, sorry, and I should say this map is going to be proper and flat, so all the fibers have the same dimension. And X is going to be three-dimensional, and it has the property that for all P in C of K, the fiber, so these are the only fibers that could possibly have rational points, because the map F is, of course, a map over K. So the fiber is going to be a Chatelet surface. I think this is a capital nu. It's not actually a V, or maybe it's a mat CCV, whatever. Such that E, capital nu, has a Brouwer obstruction. Not even a tall Brouwer, just a Brouwer-Manin obstruction to the existence of rational points. Okay? And from this setup, it's very easy to show that X can have no rational points. Easy to show, because if there were a rational point, it would have to map to a rational point of C, therefore it would have to be in this V, and therefore it wouldn't be a rational point because V has no rational points. Okay? Easy to show that X of K is not equal to, but is equal to the empty set. It's funny because being empty is a negative thing, but then I have to say equals rather than not equals when something is empty. Great. So, now, but under certain conditions, Putin was able to show that X of AK, a tall Brouwer, okay, is not empty. Question?
David? Yeah, there is a question about K. Is it an arbitrary number field?
Yeah, I believe Putin was able to do it for an arbitrary number. Yeah, Putin was able to do it for an arbitrary number field. There's going to be a condition on K in one of our results. But
okay, thank you.
Okay. And so here's part of what was key. F was not smooth. It was proper and flat, but it was not smooth. And so somehow the philosophy behind this is that, well, if you look at how you prove that there are no rational points, you do it by considering both the base and the fibers. And so in some sense, a variety is nothing more than the family of fibers over the base. In other words, if you're able to do something on the base and on the fibers, and I won't get into it, but somehow the Brouwer-Manin set of C is going to essentially just be C of K, assuming the Tate-Sheffer-Abich conjecture. And so you would expect, in theory, that if something, for example, the Untitled obstruction somehow worked on the base and on the fibers, which in a sense it does, as you can see right here, then there would be an Untitled obstruction on the whole thing. And so the idea is that if F is not smooth, in other words, F is not a fibration. And in homotopy theory, we know that if you have a fibration, then the homotopy type of the total space is essentially made up in a certain way of the homotopy type of the base and the homotopy type of the fibers. And this somehow does not work if the map F is not smooth, if there's a non-smooth fiber, which makes the map not be a fibration topologically. And so now that I'm starting to mention topology without really explaining the ideas, let's say philosophical, the philosophy of Harpaz and Schlank, which was really in response to Punin's counterexample. So they did this on the backdrop of what Putin was doing, is that all this Brouwer, a tall Brouwer, even the finite descent obstruction, are really all avatars of the Attall homotopy type. Okay? Or Attall homotopical. And if that's not entirely clear, well, a couple of things to note. First of all, the Brouwer group of X, which is already a Attall cohomology, although it's a Attall cohomology with values in some algebraic group, not with values in some least sheaf. But the N torsion, in nice cases, is going to be equal to the Attall cohomology of X with coefficients in Z mod N twisted by 1. Okay? And this is Z mod N twisted by 1 is locally constant coefficients. In other words, it can be accessed by homotopy theory. Okay? And then maybe I should say equal in good cases. Okay? And then furthermore, there's also the Attall part, which has to do with Attall covers. Okay? So Attall means Attall covers, finite Attall covers, which of course has to do with the fundamental group, which is part of the homotopy type. Okay? And that's all I'll say for now about that. So now, there's a theorem of Harpaz and Schlank. Oh, and so I should say, so Harpaz and Schlank, they developed what was known as the Attall homotopy obstruction. Attall homotopy obstruction to rational points. Okay? Like the Brouwer-Manin obstruction or the Attall-Brouwer obstruction. And then there was a theorem of Harpaz and Schlank, which was actually kind of a disappointment, is that the Attall homotopy obstruction, which they were hoping might give more information, the Attall homotopy obstruction is the same as Attall-Brouwer, at least if K is a number field. And the proof actually uses Tate-Poitou, the 9-term Tate-Poitou duality. Okay. Now, Attall homotopy obstruction works more generally over any field, but over a number field, this has to do with cohomological convention, and the Tate-Poitou sequence is the same as Attall-Brouwer. Okay? Now, what one thing that we were able to do is show that even though the Atoll homotopy obstruction gives you the same thing as the Atoll-Brouwer obstruction, we were able to use, this is of me and Schlank, we were able to use the fact that the Atoll homotopy obstruction is defined in terms of homotopy to prove something about what happens to the Atoll-Brouwer obstruction in fibrations. More specifically, when you have a map that is proper and smooth. And so here's a little theorem, which is that if we had a map as above, so if we had our F as above, where it's a more general theorem than this, but in this particular case, C is a curve, the fibers are rational surfaces. So if we have something as above is proper and smooth, which means that topologically it's a fibration, okay? And we have a couple of other conditions, one of which is that the Tate-Shafarevich group of C is finite, and another technical condition is that K is totally imaginary. So in response to over any number field, we can actually, this is because of weird topology at the real places, it turns out that if you assume the section conjecture in Abelian geometry, you don't have to make an assumption on K. Okay, which might sound kind of weird, but yes, the section conjecture in Abelian geometry comes up. Okay, so if all of this is true, okay, then in fact, Kunin's hoped for counterexample is not a counterexample. Okay, the Atoll-Brouwer set is empty, and therefore the emptiness of the set of rational points is explained by the emptiness of the Atoll-Brouwer set. Okay, and more specifically, we show that this has to be true because there's an obstruction on C. Now, C has rational points, but what this means is that essentially the Brouwer set of C is the set of rational points. So on C, and on the fibers over rational points of C. Okay, so that's sort of how we do it. And we prove a more general result. And the more general result, something that tells you that if you have a proper and smooth map, something that's a fibration, smooth and proper implies that it's a fibration. Okay, then you can relate the Atoll. Okay, so we can relate the Atoll-Brouwer obstruction on X to Atoll-Brouwer on the base and on fibers. And more specifically, you can reduce it to fibers over rational points. Okay? And the key tool that we use is that if you have a fibration, well, in homotopy theory, we like to say you get a fibration sequence of homotopy types, but in particular, you get a long exact sequence of homotopy groups. Okay? And somehow you're able to play around with those and the Atoll homotopy obstruction to get this result. More specifically, what you do is you take homotopy, you have a fibration sequence, you take homotopy fixed points, which is the kind of functor that preserves homotopy limits and therefore preserves fibration sequences, and then you get a long exact sequence on fundamental group, on homotopy groups, say homotopy groups here of the homotopy fixed points of the Atoll homotopy types. Okay, that's a technical thing if you know more about homotopy theory. Okay, and so this is how we're able to use their Atoll homotopy obstruction and the fact that it has to do with homotopy theory to prove something a little bit more concrete about the Atoll-Brouwer obstruction, which tells you something about Diophantine equations. Okay, and I believe that's all.